Very good morning, dear students. Welcome to Tungal online classes. In previous class, we have completed the theory part of electric charges and electric fields. Today, we shall start with the numerical problems of the same chapter. Yes. Before starting with the numerical problems, first let us recall the formula that we are going to use to solve the numerical problems. To begin with, we have the quantization of the charge, that is the property of electric charges, whose mathematical equation is given by Q is equal to plus or minus m into E, that is the charge possessed by any object, that is integral multiple of elementary charge of electron. So we know the magnitude of charge of electron is given by 1.602 into 10 to the power minus 19 coulombs. Here I have plus or minus m into E, that we know the object gets positively charged when it loses the electrons, and the same object gets negatively charged when it gains the electrons. So in that case, the number of electrons will be more than the number of protons present in the object. So this is the statement of quantization of the charge. Okay. Next we have Coulomb's law of electrostatics. So that states that the electrostatic force between any two charges that is given by F is equal to 1 by 4 pi epsilon naught Q1 into Q2 divided by R square. Here Q1 and Q2 are the magnitudes of the charges and R is the distance of separation between those two charges. Here we are assuming the charges are placed in air or vacuum. So I am taking it as 1 by 4 pi epsilon naught, and this epsilon naught, it is absolute permittivity or the permittivity of free space, whose value is given by epsilon naught is equal to 8.854 into 10 to the power minus 12. So what will you get here? That is, if you take epsilon naught to the left side, I can write it as Coulomb square divided by Newton square. So this is the value of absolute permittivity. By substituting this value here, this we can simply write it as F is equal to K into Q1 Q2 divided by R square, where K comes out to be 9 into 10 to the power 9 Newton square per Coulomb square. In all the numerical problems, directly we can substitute the value of 1 by 4 pi epsilon naught or K as 9 into 10 to the power 9 Newton square per Coulomb square. So this is the statement of Coulomb's law of electrostatics. Okay. Then we have something called relative permittivity. So I write it as relative permittivity. We have another term for this. It is also called dielectric constant. Dielectric constant. And we know this relative permittivity epsilon or this can also be written as capital K. That is the ratio of the electrostatic force between two charges when those two charges are placed in air, and the electrostatic force between same charges placed at same distance is placed in some other medium. Okay. So this epsilon r is equal to Fa divided by Fm, where Fa is the electrostatic force between two charges when they are placed in air, and Fm, it is the electrostatic force between same charges placed at the same distance in some other medium other than air. So this can also be written as epsilon m divided by epsilon naught, where epsilon m, that is the permittivity of the given medium, and epsilon naught, that is the permittivity of free space. Okay, so this is the definition of dielectric constant or relative permittivity. Okay, next we have principle of superposition. See here. So when I have system of charges like this, so here let me consider charge Q1 here. So here I have charge Q2. Here let me take charge Q3 here. Let me take charge Q4. Okay. So let it be plus, let it be plus, let it be minus, let it be plus. Consider charge Q1. See here. So on charge Q1, there will be force exerted by charge Q2. There will be force exerted by charge Q3, as well as there will be force exerted by charge Q4. So since these two are positive charges, the force will be something here, repulsive force between Q1 and Q2. So this I write as F12. F12 is the force acting on charge Q1 exerted by charge Q2. Similarly, between charges Q1 and Q3, you can clearly see here Q1 is positively charged and Q3 is negatively charged. Hence, there will be attractive forces between these two charges. The Q1 will be trying to move towards charge Q3 because of the attractive electrostatic force. So this force I write it as F13. F13 is the force exerted on charge Q1 by the charge Q3 here. Similarly, when I consider the pair of charges Q1 and Q4, we can clearly see here both are like charges. They are positively charged here. They are positive charges. So there will be repulsive force between charges Q1 and Q4 here. So this charge Q1 will be trying to move away from charge Q4 because of the repulsive force between Q1 and Q4 here. So this force I write it as F14. Right? Similarly, if I consider other charges also, there will be same number of forces acting on each and every other charge here. Okay, but here I consider only charge Q1 here. So the principle of superposition, it states that the net force, the net electrostatic force acting on charge Q1 because of the system of charges is the vector sum of individual forces exerted by each charge here. So that I can write as F1 is equal to F12 plus F13 plus F12. Here I have only 4 forces here. So on any one of the charges there will be total 3 forces acting. The net electrostatic force acting on charge Q1 is the vector sum of individual forces exerted by other 3 charges in this example. If you have n number of charges like this, so the net force will be sum of n minus 1 number of forces. Okay, so that is the statement of principle of superposition. So this is very useful when solving numerical problems for system of charges given in the numerical problem. Okay, so next we have electric field intensity. So that is given by force exerted by unit positive charge. E is equal to F divided by Q here. If I consider a source charge of capital Q here, if I want to calculate what is the electric field intensity of this source charge at any point P here, so at point P usually I will consider a unit positive charge. So this is the distance here, right? So electric field intensity of this source charge, so that can be written as E is equal to F divided by Q, and by simplifying this we can get it as E is equal to 1 by 4 by epsilon capital Q divided by R square, where R is the distance between the point of concentration and the source charge here. So this is the formula for electric field intensity of any given source charge. Wherever you are finding electric field intensity, at that point we consider a unit positive charge here. Okay, so that is the definition of electric field intensity. The principle of superposition is applied for electric field intensity also. That is, see here if I have only one charge here, so let me write capital Q1 here, let me consider another charge capital Q2 here. So at this point there will be electric field because of charge Q2 also, there will be electric field because of charge Q3 also here. So the net electric field intensity at point P is the vector sum of electric field intensities exerted at this point P due to all individual source charges. In this example, I can write it as electric field intensity at point P because of source charge Q1, Q2 and Q3, that is the vector sum of E1 plus of E2 plus of E3, where E1 is electric field intensity at P because of charge Q1, Q2 E2 is the electric field intensity at point P because of charge Q2 here. Similarly, E3, that is the electric field intensity at point P because of source charge Q3 here. Source charge need not be always positive charge here. Source can either be positive or negative. If the source charge is positive, the electric field intensity will be moving outwards. If the source charge is negative here, so let us say Q3 negative here, so the electric field intensity because of charge Q3, that will be moving towards test charge here. Okay, so this is the application of principle of superposition. superposition for calculating the net electric field intensity at any point for a system of source charges given. Okay. Then we have for electric dipole, now consider electric dipole. Electric dipole is a system of two equivalent opposite charges. Right? So if at A I will be having plus Q charge, at B I will be having minus Q charge, which are separated by certain distance. That distance is also called the dipole length. Okay? So this 2A is called dipole length here. So the dipole moment of electric dipole is given by P is equal to Q into 2A. Okay? So that is equal to magnitude of any one of the charges into the distance between both the charges or the dipole length, which is equal to 2A here. Okay, so this is the magnitude of electric dipole moment, and the direction of electric dipole is always from negative charge to positive charge. Okay, so then if an electric dipole is placed in an uniform electric field, see here, see the uniform electric field of magnitude E here. If I have some plus 2 charge, if I have minus 2 charge, these two equivalent opposite charges form an electric dipole. When an electric dipole is placed in a uniform electric field of magnitude capital E here, so there will be some rotational effect experienced by the dipole. So that torque experienced by the dipole is given by P into E into sin theta, where P is the dipole moment of this electric dipole and capital E, that is the magnitude of electric field intensity of this external electric field, and theta is angle between so this dipole and the direction of electric field. Tau is equal to TE sin theta here, and we know tau is maximum when this theta is equal to 90 degrees or sin theta is equal to what? 1 here. Okay. Then by Gauss law, the electrostatic flux is given by 1 divided by epsilon naught into Q. Yes, so that is the definition of electric flux. Okay. Then let us start with the numerical problem here. I hope you can clearly see this. Just let us go through the problem given. They have given that 2 point charges each of 0.65 microcoulomb are separated by a distance of 0.5 meters here. So this is the magnitude of the charge given. Both the charges are having magnitude of 0.65 microcoulomb. Okay, and the distance of separation is given to be 0.5 meters here. Okay, and what they are asking to find out: number one, what is the force of repulsion? Since both charges are like charges here, definitely there will be repulsive force between both the charges. So first, number one is what is the force of repulsion? We have to find out using Coulomb's law. Number two, what is the force of repulsion if each charge is doubled and the distance between both the charges is halved here? So that is separate case. Okay. Then third case we have what is the force of repulsion if they are placed in water whose dielectric constant is 80. Okay. So gradually we shall start with part 1 here. So number one, what they are asking to find out. So first, let us write down the data given. So here we have system of two charges here. So first charge they have given to be Q1 is equal to what? 0.65 microcoulomb they were given. Okay. Second charge Q2 that is also equal to what? 0.65 microcoulomb. And the distance of separation between both the charges is given to be how much is that? That is R is equal to 0.5 meters. Correct? So first we have to find out what is the force of repulsion. Okay. Since both charges are positively charged, so there is repulsive force between both the charges whose magnitude is given by Coulomb's law of electrostatic. So that I can write it as F is equal to 1 divided by 4 pi epsilon naught Q1 into Q2 divided by R square. The basic equation I am using here. So by substituting the values, I know 1 by 4 pi epsilon naught is what? So that is 9 into 10 to the power 9 into Q1 is equal to what? So that is 0.65 into 10 to the power minus 6. They have given it as a microcoulomb. So this micro I write it as a into Q2 is also same here. Both charges are equal. So that I write as 0.65 into 10 to the power minus of 6 whole divided by what is the distance between them, that is 0.5 meters. So that I take it as R, but I have write R square here. So that I write it as 0.5 square. Okay. So how to solve this here? See here. First what to do? You simplify all the numerical values. 10 raised to power, so later you can add. So by simplifying this, I can write it as F is equal to what? This I can write it as 9 into 0.65 into 0.65 whole divided by 0.5 square is equal to what? 0.25 into 10 raised to power of. Here I have plus 9. Here I have minus 6 into minus 6. So that is minus 6 plus of minus 6. So this here I am using the formula. That is a raised to m into a raised to m is equal to what? A raised to m plus of n here. So I can simply add the powers of 10 here. 9 minus 6 that is 10 to the power minus 3 here. So by simplifying this, so this force I will get it as 1.52 into 10 to the power minus 2 newtons. So this is the force of repulsion between both the charges given. Okay, so first part we completed here. Then look at what I will do in the second part here. What is the force of repulsion if each charge is doubled and the distance between them is half they are giving here? Okay, so now what happens here? Look at this. The magnitudes of the charges are changed. So Q1 dash. So let me write the new charge is equal to what? It is no more Q1. So Q1 is changed to Q1 dash. So that Q1 dash is equal to what? So this magnitude is doubled there. Each charge magnitude is doubled. So this Q1 dash, that is the new magnitude of the charge, that I can write it as Q1 dash is equal to what? 2 times of Q here. Similarly, Q2 dash I write it as 2 times of Q2. Correct? So Q1 dash I write it as 2 times of Q1. Q2 dash I write it as 2 times of Q2. Not only the magnitude of the charge, the distance between both the charges is also changed. What the distance change? The distance is what here? The distance is half they are telling you. So it is reduced to half of the initial value. So if initial value is taken to be R, so here I can write it as the new distance can be written as R dash is equal to what? R by 2 here. Is it not? So when the magnitudes of these charges as well as the distance between both the charges is changed, definitely the electrostatic force of repulsion will also change here. So that new force I write as F dash is equal to what? 1 divided by 4 pi epsilon naught. So let me write it as Q1 dash into Q2 dash whole divided by R dash square. What I am doing here? I am replacing this Q1 by Q1 dash. Right? I am replacing this Q2 by Q2 dash and I am replacing this R by R dash. What is that I am doing here? So just simplify this, what you get? 1 by 4 by epsilon naught. So this Q1 dash is equal to what? So this I can write it as 2 times of Q1. Yes? And Q2 dash I can write it as 2 times of Q2 here whole divided by R dash I can write it as R by 2. But in here I have the square here. So in place of R dash I will write it as R by 2. So here I have the square. Correct? Then simplify this, what you get? F dash is equal to what? F dash is equal to 1 divided by 4 by epsilon naught. Here I have 2 into 2, 4. So this denominator of the denominator that comes to the numerator. So here in the numerator I will have 4 into 4 Q1 Q2 divided by R square. So this can be written as total I will have 16 times of 1 by 4 by epsilon naught Q1 Q2 divided by R square. And look at this. What is this 1 by 4 by epsilon naught Q1 Q2 by R square? That is the initial value of electrostatic force. For the first part, whatever I have calculated, so that is the electrostatic force. So simply I can write it as F dash is equal to what? 16 times of initial value of the electrostatic force of repulsion here. So I can simply write it as 16 into whatever the value of F we have got. So that is 1.52 into 10 to the power minus 2 newtons here. So this comes out to be, yes, it is around 0.243 newtons here. So this is the new value of electrostatic force of repulsion repulsion when the magnitudes of the charges as well as the distance between both the charges is changed. Yes, so that is the new value of the force. So second part also we have calculated. Then third part, what they are asking here, what is the force of repulsion if they are placed in the water whose dielectric constant is AT. Okay, third part what they are doing here. Yes, we know the dielectric constant or relative permittivity that is given by force between two charges when they are placed in the air. So far whatever solution we have done, whatever force we have calculated, that is assuming that both the charges are placed in air. Okay, so by the definition of dielectric constant, I can write K is equal to what? Fa divided by Fm, where Fa is the force between two electric charges when they are placed in air, and Fm, it is the force between same charges placed at same distance in some other medium. In this example, they have given that different medium, that is nothing but water, and its dielectric constant is given by K here. So easily I can calculate the force between the same charges when they are placed in water that are rated as F medium. So that is equal to Fa divided by Fm. Here Fa, I have to take the first value here. Do not take second one. Second one is separate case. So original value of repulsion, so that I have to calculate, that is first one. So that is equal to 1.52 10 to the power minus 2 newtons. So that value I have to consider. So Fm is equal to what? So this I substitute the value of Fa 1.52 into 10 to the power minus 2 newtons whole divided by. So here I have to write Fm is equal to Fa divided by K ampere. Sorry for that. So divided by K is how much? That is going to be 80 here. So the electrostatic force of repulsion when the same charges are placed in water, so that is calculated as 1.52 10 to the power minus 2 divided by 80. So that is equal to 3. Yes. So that is equal to 1.9 into 10 to the power minus 4 newtons. Just calculate this value and verify the answer here. So that comes out to be 1.9 into 10 to the power minus 4 newtons. Okay, so all parts we have solved. This is part 1, part 2 as well as part 3 we have completed. Okay, so that is the solution for our first problem. Okay, then look at the second problem here. Yes, here the problem and write down the data given. What they are given there? The electrostatic force between two like ions. They have given two like ions here. Both charges are same, that are separated by 5 angstroms. The distance of separation between both the charges is given, and that value of the repulsive force is equal to what? 3.7 into 10 to the power minus 9 newtons. Okay, what they are asking to find out? We have to find out what is the charge on each ion they are asking. Okay, how many electrons are missing from the each ion? See here, they have clearly mentioned how many electrons are missing. That definitely indicates these ions are positively charged. Is it? So they have given the electrostatic force. I have two charges here, right? So between two like ions. So they have given the first charge is what? Q. The second charge is also equal to what? So that also I can take it as Q here. The distance of separation between these two charges is going to be 5 angstroms. So that I can write it as R is equal to angstrom is nothing but 10 to the power minus 10 meters. Correct? And the force of repulsion between these two charges is going to be what? F is equal to 3.7 into 10 to the power minus 9 meters. That is the force of repulsion. I have to find out what is the magnitude of charge of each ion they are saying. Okay? Then, so let me write it from by Coulomb's law. I write it as F is equal to 1 by 4 pi epsilon naught Q into Q divided by R square. Okay? So I just have to find the value of Q square here. So this I write it as Q square is equal to what? Right? Or I can substitute the values here. Yes. F is equal to how much? 3.7 into 10 to the power minus 9 here given. 1 by 4 pi epsilon naught, that I can write as 9 into 10 to the power 9 here into q square I can write here divided by r square is how much? 5 into 10 to the power minus 10 whole square I have to write. Okay. So to simplify I can write it as q square is equal to what? So this I get it as 3.7 10 to the power minus 9 into 5 into 10 to the power minus 10 whole square, yes, whole divided by, this also I will take it to left side here, so that goes to the denominator, that I write as 9 into 10 to the power 9. Okay, simplify this, what I will get? 3.7, 5 square I have to take here, 25, whole divided by 9, and 10 raised to power separately I have written here, 10 to the power minus 9, 10 raised to minus 10 square. I know the formula a raised to m whole raised to n. How do you write it? So this can be written as a raised to m into n. Okay. So here I can write it as into 10 to the power minus 10 into 2 I write it here. So this I write it as 10 to the power of minus of 20. Okay. Whole divided by 10 raised to 9 here. Okay. So when I substitute the values here by simplifying, I can get it as q is equal to this. This q comes out to be around 3.206 into 10 to the power minus 19 coulombs. This is the value of charge present on each ion. After simplifying this numerical values, I get the value of q is equal to 3.206 into 10 to the power minus 19 coulomb. That is the charge present on each ion. Okay, so first part we have done. That is, what is the charge on each ion that we have calculated? Q is equal to 3.206 10 to the power minus 19 coulombs. Then they are asking how many electrons are missing from each ion. Clearly the charge is positively charged. Okay, hence the object has lost the electrons. By quantization of the charge, I can write Q is equal to what? N into E. So N I can write it as Q divided by E. So that is equal to 3.206 into 10 to the power minus 19 whole divided by charge of one electron is equal to what? So that is 1.602 into 10 to the power minus 19. So this comes out to be 2 here. So the number of electrons missing from each ion, that is nearly equal to 2. This is the solution of a given problem. Okay, look at the next question, dear students. What they are given here? The electrostatic force on a metal sphere of charge 0.4 microcoulomb due to another identical metal sphere, they are telling, of charge minus 0.8 microcoulomb in air is 0.2 newtons. There are two metal spheres. So first one, let me call it as metal sphere A. Second one, I will take it as metal sphere B. They have told both are identical metal spheres, which indicates that both have same size and shape. The surface area of metal sphere A is same as the surface area of metal sphere B. Let the distance of separation between these two metal spheres, let it be r here. Okay, and the charge of metal sphere A, let me write it as q1. q1 is equal to what? They have given 0.4 microcoulomb, and q2 how much they have given? q2 is equal to what? Minus of 0.8 microcoulomb they have given. Okay, and they have also given the force between these two metal spheres is how much? That is 0.2 newtons. Okay, then they are asked to find out what is the distance between two spheres. Okay, so using this data I have to find out what is the distance r. Easily I can find out using the Coulomb's law of electrostatics. So that I simply write it as F is equal to what? 1 by 4 pi epsilon naught q1 into q2 divided by r square. Okay, by substituting the values I can easily find the value of r square here. Yes, r square is equal to what? 1 by 4 pi epsilon naught q1 into q2 divided by f. Substitute the values here. What I will get? R square is equal to 9 into 10 to the power 9 into q1 is how much? That is 0.4 microcoulomb, 0.10 to the power minus 6 into the charge of second sphere is how much? That is 0.8 into 10 to the power minus 6 whole divided by 0.2, which is nothing but the force between these two metal spheres. Okay, By solving this, I can get the value of R. So that is equal to 0.12 meters. By calculating with all these numerical values, the value of R is equal to how much? 0.12 meter. Okay. So this is the first part of the problem here. They have asked to find out the distance between two spheres. Then the second part is something different here, and also the force between same two charges when they are brought into contact and then replaced in their initial positions. See here what they have done is, so initially whatever these metal spheres were at the distance of R, which is equal to how much? 0.12 meters. What they have done? They have brought both the metal spheres into contact with each other. So what happens whenever these metal spheres are brought into contact with each other? So here we have to consider the concept of redistribution of the charges. What happens whenever we have some two identical metal spheres like this? So when they are away from each other, let us say the charge present on first metal sphere, let it be QA, the charge present on second metal spheres, let it be QB here. Okay. So when I have charge of A, that is QA, charge of B, that is QB, when they are brought into contact with each other, so there will be transfer of charge from one object to another object. Okay. And when these two spheres are separated again, the spheres will have new values of electric charge. Okay. That new value of electric charge, that I write it as QA dash. So here I write it as QB dash. Yes. The redistribution of these magnitudes of the charges will be such that QA dash will be equal to QB dash will be equal to, that will be QA plus of QB divided by 2. So this is how the charge gets redistributed when both the spheres are brought into contact with each other and when both the spheres are separated again. Okay. The new charge on each sphere will be equal to what? QA plus QB divided by 2. For this we have the condition that both the metal spheres must be identical. They should have same size and shape here. Okay. So by using this concept, what we can do here is the new charge. So here also they have done the same thing. These metal spheres are brought into contact with each other and then again they are placed at the same initial distance of 0.12 meter. Read here what they have done. Find, yes, and also the force between same two spheres when they are brought into contact and then replaced in their initial positions. So for the new charge present on QA dash, the new charge present on metal sphere A, that I write as Q1 dash, that is equal to what? Q2 dash. So that will be equal to Q1 plus Q2 divided by 2. Okay. So what is the value of Q1 here? Q1 is equal to what? 0.4 microcoulomb. Q2 is equal to what? Minus of 0.8 microcoulomb whole divided by 2. So this I will get it as minus 0.4 divided by 2. So the new charge present on both the spheres, that will be equal to what? Q1 dash is equal to Q2 dash, that is equal to minus of 0.2 microcoulomb. This is the new charge present on both the spheres when they are separated after getting them into contact with each other. Okay. So whenever the magnitudes of the charges are changed, definitely the force will also change. That new force we have to find out. So that new force I write it as F dash. F dash can be written as 1 by 4 pi epsilon naught Q1 dash Q2 dash divided by R square. You can observe here there is no change in the distance between both the spheres. Okay. Substitute these values so that I get it as 9 into 10 to the power 9 into Q1 dash is how much? Yes, Q1 dash, that is also equal to 0.2 here into 10 to the power minus 6 into 0.2 into 10 to the power minus 6. So while substituting, we just have to substitute the magnitude of the charge. Do not write negative sign here. Okay. Divided by R square is how much? R is equal to 0.12 we have found out. So substituting the value of R square, that is equal to 0.12 square, I can get the value of F dash. By simplifying this, how will you simplify this? Just write the numbers separate. 9 into 0.2 I write it here. Again I will write 0.2 here. Whole divided by 0.12 square into 10 raised to powers. I write them separately. 9 into 10 raised to 9 into 10 raised to minus 6, that will be minus of 12. Right. So at the end I will get, so this implies the new force F dash will be equal to what? So that is 0.025 Newton. So this is the new value of the force because of change in their electric charges. Okay, so this is the solution for problem number 3 here. Yes, I hope it is clear. Next, look at question number 4. Read it carefully and write down the data given. What is given there? Check it out. ABC is an equilateral triangle of side 0.03 meter, charges of plus 5 nanocoulomb, plus 3 nanocoulomb and minus 5 nanocoulomb are placed at corners A, B and C respectively. Okay. Find the resultant force on charge at B. Okay. So for this, what we shall do? First, let me draw the equilateral triangle given. Yes. So this is the equilateral triangle given. Let me write this as A. Let this be B here. Let this be C. Okay. You can write in any order. There is no rule for writing it clockwise or anti-clockwise. But be careful. Whatever charge is given at point A, so that you have to write it at A. Similarly, we have to do it for point B as well as point C. Yes. So what is the charge given at A here? So that is, so let me write it as Q1 is equal to what? Plus 5 nanocoulomb they have given. Okay. So similarly, charge at B, I write it as Q2. Q2 is equal to how much? Plus 3 nanocoulombs. Similarly, the charge at point C, so that I write it as Q3. Q3 is equal to how much? Minus 5 nanocoulombs. Correct? So these are the magnitudes of the charges given. Yes. And what they are asking to find out? Find the resultant force on a charge at B. What is the charge at B? So that is nothing but Q2 here, which is having magnitude of plus 3 nanocoulomb. Yes, at the beginning of the class, we have discussed the concept of principle of superposition. So what does it state? So whenever we have system of charges, the net force, the net electrostatic force acting on any one of the charges is the vector sum of forces exerted by individual charges. So in this case, when I consider the net force acting on Q2, that net force will be equal to the vector sum of force exerted on charge Q2 because of charge Q1 and the force exerted on charge Q2 because of charge Q3 here. Okay. Let us show the directions of the forces exerted on charge Q2. Yes. So look at this. Q2 is positively charged, correct? And Q1 is also positively charged. So there will be repulsive electrostatic force acting between Q1 and Q2 here. So this Q2 will be moving away from charge Q1 because of this electrostatic repulsive force. So this force direction I will show it along AB extended. So that force I read it as F21. F21 is the force exerted on charge Q2 because of charge Q1. Clearly, it is along the direction AB extended. This charge Q1 will also be moving along negative x direction, but I am not interested in calculating that force. I just want to know what is the net force acting on charge Q2. Okay. Then let us consider the pair of charges Q2 and Q3 here. You can clearly observe Q2 is positively charged and Q3 is negatively charged. Hence, there will be attractive force between Q2 and Q3. Okay. So in what direction does the charge Q2 move? So Q2 will move definitely along BC here. So this charge Q2 will be trying to move towards Q3 because of the attractive force. So there will be attractive force between these two charges. So Q2 will be trying to move towards the charge of Q3. Okay. So this force I read it as F23. So this is the force exerted on charge Q2 because of charge Q3. Okay. Then let us write the magnitudes of the forces F21 and F23 using Coulomb's law of electrostatics, that I can write it as F21. F21 is equal to what? That is the electrostatic repulsive force between charges Q1 and Q2, or it is the force acting on charge Q2 because of charge Q1, which is given by 1 divided by 4 pi epsilon naught. What are the charges we have to consider? There is this Q2 and Q1. So that I write it as Q2 into Q1 whole divided by what is the distance between charges q1 and q2 here? That is nothing but AB. So this I write it as AB square. So when I substitute the values, F21 I can write it as 1 by 4 pi epsilon naught. So, or you can simply write it as 9 into 10 to the power 9 into Q2 is how much? 3 into 10 raised to minus 9 into what is the magnitude of charge Q1 here? That is 5 into 10 to the power of minus 9 whole divided by what is the distance given? So the distance is given to be how much? 0.03 meters, and all sides are equal since it is equilateral triangle here. Okay, so substitute the value of AB square, so that is equal to 0.03 square here. Yes, by simplifying these numerical values, I can get it as F21 is equal to how much is that? That is 1.5 into 10 to the power minus 5 newtons. So this is the force acting on charge Q2 because of charge Q1. Okay. Similarly, when I consider the force F23, right? So F23 I write it as F23 is equal to what? 1 divided by 4 pi epsilon naught. What charges I have to consider? Q2 and Q3. Q2, Q3 divided by what is the distance between charge Q2 and Q3? So that I write it as BC square, is it not? So that is equal to what? BC square. So that comes out to be how much? 1 by 4 pi epsilon naught. I can write it as 9 into 10 to the power 9 into Q2 is how much? 3 into 10 to the power minus 9. And what is the magnitude of charge Q3? That is 5 into 10 to the power of minus 9. Observe here, I am not writing the negative sign of this minus 5 nanocoulomb, because already that concept already I have considered while taking the direction of F23. Why I am writing F23 from B to C? Because already this is negative charge and this is positive charge, so there will be attractive force. Already that concept I have considered here, so do not write negative sign with 5 nanocoulomb here. Okay, so divided by BC square is how much? That is 0.03 square. Observe these two equations. Both the charges are same. Here I have 5 nanocoulomb, 3 nanocoulomb. Here I have 5 nanocoulomb, 3 nanocoulomb, and the distance is also same here. So the magnitude of these forces will also be same. So that I write it as F23 is also equal to how much? 1.5 into 10 to the power minus 5 Newton. And what is the direction of this force? So this will be acting along, this force F23 will be acting along BC. Okay, and this F21 will be acting along, this will be acting along AB extended. Okay, so this I can write it as this force is acting along AB extended along positive x direction. Okay, now see here the same figure I will draw it again here. So this is the equilateral triangle. So this is the charge Q2 here. There is one force acting along positive x direction. So that is what? That is equal to what? F21. And there is another force acting from, this is A, this is B, and this is C here. The force F23 is acting along B to C, so that I write it as F23 here. Okay, see here I have two forces acting on the charge at angle of 120 degrees. Since it is equilateral triangle, the interior angle is 60 degree and this angle comes to be 120 degrees. In first year classes we have calculated what is the resultant force. Okay, the same concept I can use here. So along with that, what I will do here, so what we can write, see here I can write F21. You can clearly observe F21 is equal to F23, so that I can write it as F21 is equal to F23. Simply better write it as F here. Okay, so to avoid the substitution of the numerical value, so I am writing both equal to F, so which makes my work easy here. So if I write the resultant force between these two vectors is equal to what? Square root of, that I write it as F1 square plus of F2 square plus 2 F1 F2 cos of theta, where theta is angle between both the forces F21 and F23. Correct? So when I substitute these values, this I write it as Fr. So what is F1? So this I can write it as F21. So this I can write it as F23. This I write it as F21 and F23. That was the general formula I have written. In this case, instead of F1 I have F21, instead of F2 I have F23. Same values I have replaced here. Okay, so when I substitute F21 is equal to F, so what I will get here, instead of F21 I can simply write it as F square plus of F23 is also same as F square plus of 2 into F21 is equal to F. F23 is also equal to what? F. And what is the angle between these two forces? That is 120 degrees. So that I write it as cos of 120 degrees. So when I simplify this, Fr is equal to, the magnitude of Fr is equal to square root of, so this is 2F square plus of F square, that is 2 times of F square cos 120 degree. Cos 120 degree is equal to what? That is minus of cos 120 degree is equal to minus of 1 by 2, because we are using the concept of allied angles, that I like it as cos 120 degree can be written as cos 180 minus of 60 here. In second quadrant cos is negative, so that I use as a minus of 1 by 2. So when I substitute it here, so this will be equal to 2 into F square into minus of 1 by 2. So after simplifying, I will get it at square root of F square. So a resultant force will be equal to, and magnitude of resultant force will be equal to what? So that is square root of F square, so that is equal to F. F is equal to how much? That is again 1.5 into 10 to the power minus 5 newtons. This is the resultant force acting on charge 2 because of charge 1 as well as charge 2, charge 3 there, Q1 and Q3. And what about the direction of this resultant force? You can clearly observe here, F21 is equal to F23. So the resultant force will be bisecting the angle between these two forces. So your resultant force will be somewhere here. So this is your Fr. So this makes angle of 60 degree with F23. That is the direction of resultant force of Fr with respect to F23. Okay. So this is the solution of given problem, and this is the direction of resultant force, which is at angle of 60 degree with respect to the direction of F23.